Good evening, everyone. Okay. Yeah, I'm Kyungsun Lee, postdoctoral researcher in KIAS, and thank you for the organizers to give me an opportunity to give this talk, and also thanks to all for staying until this late part of today's program. And today I will show some multisymplectic framework. How this multisymplectic framework provides a new perspective on the branes, and how the symmetry or constraints or higher algebraic structures fit together into this multisymplectic geometry. So this work is based on the ongoing projects with Professor Eun Jung and his student Min-Kyu Cho in Kyung University, and Karapan Mikrosan in Imperial College London. So yeah, sometimes when I give a talk that drifts too far from the conference title, like String in Soul, I often feel some guilty, but tonight I think I can sleep very well. Yeah. So let's get started. So before diving into the strings and branes, let me first remind you the first order formalism of the point particle action, or in other words, the word line action. So if you see the first term, you can see the canonical form, which is nothing but the p mu dx mu. And in the second term, the Lagrange multiplier is multiplied by the Maxwell relation. You can easily read out this symplectic 2 form from this canonical 1 form. And you can also easily see the constraints from this Maxwell relation. And by varying with the p mu, we have equation of motion which has this form. And by plugging back this p into here and integrating out the lambda, we reach into our familiar word line action, which has such scale root form. So far, there's nothing special in this slide. So now let's move on to the wordsheet action. Actually, the first order formalism of the string, which is familiar with, is the Polyakov action. But here you can see some seemingly unfamiliar form is sitting in this box. So let's see in detail. So in the first term, as we are seeing some wordsheet action, there's dx mu and dx mu, which is coupled to the p mu nu, which would be some antisymmetry. And also in the second term, we just put the p mu nu square plus some constant. And this action exactly mirrors the point particle case. But here from now, actually the canonical symplectic form is not the 1 form, but the 2 form, so that the symplectic form becomes the 3 form like this. And with these constraints and doing the same work as in the point particle action, we also arrive at some Nambu-Goto action, which has such scale root form. And furthermore, we can do the same things for some generic p-brane, and we would again get some p-brane Nambu-Goto action.
What do we do?
I will show how we will do with this multisymplectic form. But the question is, does this formalism actually make sense beyond just reproducing this Nambu-Goto action? More precisely, how far can we push this multisymplectic framework as a natural extension of the symplectic geometry? This is about some first term. And the second question that we can draw is, what constraints are truly admissible and how generic can they be? This is about the second term in here. So these two are the guiding questions that I'd like to explore in the rest of this talk. So let me give you some outline. So first, I will review the multisymplectic geometry, which is not that familiar to many audience, including some graded Poisson structure or some L infinity algebras. And then I turn to some canonical multisymplectic form and its Hamiltonian forms associated to the Poincare symmetries. And by combining all these ideas, I'd like to construct the consistent, some compatible constraints on the branes. So this is the outline of the talk. And let me begin with the multisymplectic geometry. So let me first review the symplectic geometry to remind you some notions and properties. So like the metric tensor is the key player in the Riemannian geometry. And in symplectic geometry, the non-degenerate closed two form is the main characters. And with this symplectic two form, we can make a Hamiltonian function which induces this Hamiltonian vector field by this Hamilton equation. But in here, as this omega symplectic form is two form, but X is vector field, so that the left-hand side is one form, and this Hamiltonian function should be some function or zero form. And by plugging these two kinds of vector in this symplectic two form, we can define the Poisson brackets. And as we all know, this Poisson brackets satisfy Jacobi identity. And combining all other some properties, you can prove that this Poisson algebra is a Lie algebra. But what if we allow the symplectic form to have some higher degrees for, say, P+2 form or something? First, let's consider the 3 form case, which is relevant to the string case. So, yeah, as now this omega is 3 form, so that not only the vector, but also the two vectors can be inserted into this 3 form, which would give a eta as some zero form. Of course, we can also insert the vector into here, so that the left-hand side becomes the 2 form, and eta on the right-hand side becomes 1 form. So this is the summary. So if we insert as a vector, it would give a 1 form eta. And if we plug in this 2 vector in here, then it will give us some Hamiltonian function. So the funny thing in this multisymplectic setup is that not only the Hamiltonian function is allowed, but also some Hamiltonian forms can be defined with respect to some higher multivectors. So keeping this thing in mind, we can write the graded brackets of the form like this. This is familiar in the this looks like just a Poisson brackets, but in this multisymplectic setup, eta can not only be some zero form, eta can be a 1 form. So 1 form can be inserted in here. And another funny thing is that as this omega is a 3 form, we can insert the 3 kinds of vectors. So not only these binary brackets, we can define these ternary brackets. So the natural brackets in this multisymplectic setup is like this, which can allow some various grade or various degree, and which also allows some inputs greater than 2. And with this proper sign vector, we can define this graded Poisson brackets like this, and it satisfies such graded anti-symmetry. But so far so good, but what happens to the Jacobi identity? So in the symplectic geometry, Jacobi identity exactly holds, so that the Poisson algebra equals Lie algebra. However, in this graded Poisson brackets, even though they satisfy the graded antisymmetry or graded Leibniz-Knoll rule or etc., the graded Jacobi identity does not hold exactly. So it is violated by up to this exact term. But this violation is not the failure. And this is the signal of the higher algebraic structure, which is called L-infinity algebra. So L-infinity algebra is some graded vector space with this multilinear maps satisfying the generalized Jacobi identities, which has the non-zero but exact term on the right-hand side. And generically, such exact term is controlled by some higher brackets. So if you see in here, the left-hand side is only composed of the binary brackets, but on the right-hand side, you can see that this is the ternary brackets. And this sequence go and go and go, and so that such chain continues infinitely. So we call this structure, algebraic structure, as the L-infinity algebra. But this is the generic definition. But if we restrict to some string or brane, which is p equals 1 or generic p, the chain stops at a certain point. So in case of the p equals 1, the chain stops at ternary brackets. Physically, this is because we have street form, multisymplectic street form. We can only insert up to 3 vectors into the multisymplectic form so that it stops at the ternary brackets. Likewise, you can generalize into the p plus 2 form, and it is called some Lie p plus 1 algebra. So the first big question that I asked was, do these multisymplectic frameworks make sense or not? And the answer is yes. And multisymplectic geometry is some natural extension of symplectic geometry with such higher or very complex algebraic structure. And by allowing some higher degrees and by allowing the many more inputs, it can have some graded Poisson brackets, and it leads to the L-infinity algebras. However, because of such complexity, it is important to look at some explicit example. So that is the point I will present in the next slide. So I will turn to this canonical multisymplectic form and some Hamiltonian forms of these Plancke symmetries. So the canonical multisymplectic form that we will start is this form. So in the usual symplectic geometry, some Darboux theorem guarantees that such form is always possible. However, as far as to my best knowledge, this Darboux theorem is not guaranteed in this multisymplectic geometry, but nonetheless, we can check whether this is closed or whether it is non-degenerate. But this simple form is trivially closed and non-degenerate. And we can also find some Hamiltonian vector fields that preserves this multisymplectic form. So this can be solved by acting the Lie derivative into this multisymplectic form. So for translations, the Hamiltonian vector field is quite simple, which is nothing but the derivative of the coordinates. And for Lorentz symmetry, it has very familiar form like x dx or p dp, where this tilde derivative is derivative with respect to some generalized momentum. And you can check that with these Hamiltonian vector fields, these ensure to preserve this multisymplectic form for, you can easily check this so that we can it is sure that these are the Hamiltonian vector fields. So also we want to explicitly write down the Hamiltonian form with respect to such Hamiltonian vector fields by using this Hamiltonian equation. You can also easily solve this from the Hamiltonian vector fields like this form, where the translations, the conserved quantities in this for these translations now has the form, the generalized momentum contracted with some world volume sector. And for the Lorentz symmetry, it also has some familiar form like xp minus px term contracted with some volume form. So now let's turn to now combining all these ideas. Now I'd like to construct single out some possible constraints that can be imposed in the Branes system. So I'd like to impose the two conditions for the compatible constraints. The first condition is the compatibility with the space-time symmetry. This is nothing but some commutativity with some Hamiltonian forms of the Frankreich symmetries. And the reason that we impose is that if it fails to commute, then it means that it will break some Frankreich symmetry so that the reduced phase symmetry do not respect such space-time symmetry. So we should impose such condition if we want some resulting theory to preserve such space-time symmetry. And the second condition that we would like to impose is to ensure this constraint to generate the redundancy flows. In other words, we would like to define the constraints which satisfy such Hamiltonian equation. This is because otherwise it will not give us some if this is not satisfied, it would just be some arbitrary condition. And the reason we impose this is to make this constraint to generate a flow. And we would like to quotient by that flow to get the reduced phase space. And another way of viewing of this condition is that this ensures that some variation of the canonical form with respect to this zeta becomes total derivative even before imposing the equations of motion. So this is the feature of some gauge systems. So we'd like to impose such both conditions to the constraints. And as I have emphasized in the first part, the constraints can be any Hamiltonian form in general, not just the Hamiltonian function. And to maintain some non-degenerate relationship between P and its conjugate, we will restrict some constraint to up to quadratic order in P. So our task is to start with the most generic multivector ansatz for zeta, which would generate the constraints and also satisfy such space-time symmetry. So as we are dealing with some P+2 multisymplectic form, we can allow up to P+1 multivectors. So this is the generic ansatz form of multivectors that allows up to P+1 degrees. So first term has some unknown coefficients f with space-time derivatives. And second term has some undetermined g with derivative of p and other space-time derivatives. Maybe you can think of the more terms like with more tilde del P. But as we are starting with the canonical multisymplectic form, it will not affect our results. So now let's impose these conditions step by step. So by imposing the compatibility with the translation, which is nothing but this expression, it turns out that the only f mu 0 to mu p, or in other words, all these possible g cannot be satisfied, and only this term survives in the ansatz. And by writing down these Hamiltonian equations for the constraints, it turns out that this undetermined f would only dependent on the generalized momentum p. Also, by imposing the compatibility with the Lorentz symmetry, it turns out that this unknown f is just proportional to generalized momentum p. So putting this together, the final form of the Hamiltonian multivector that generates the compatible constraints has the form like this form. And there's some compatible constraints that flow with this multivector is that we have such quadratic constraints where this constant is fine-tuned to give exactly the number to xn. So I hope, yeah. P plus 2 point. Yeah. So I hope you are happy with this expression, and let me pause with some remarks and open questions.
Before we do the quantity,
There's, yeah, you'd like to, yeah.
If you try to do path integral with this exponent, you know what?
So far, we don't have any idea for the quantization, yeah.
But I mean, motivation for this is higher dimension of where we come.
Right. And so far, yeah.
Framing that classically gives you looks like the volume determinant that. Right. Like we know how to put ordinary quantum field theories in Hamiltonian form. Do you know how to put any action for like a standard quantum field theory into this form?
Yeah, in the case of the same quantized field theories, I don't know. I don't have no idea for writing like this. But there exists some de Dondorf formalism that fits into such field theory. But in this formalism, I don't know how to implement it.
So with this p equal 3 or p equal 2, equal 2, if you integrate out p's, you do end up with number of like volume.
Yes. Yeah, right.
So if you can quantize this,
then yeah. So I will conclude with the remarks. So still, there's no some precise formulation for some multisymplectic reduction, or I just heard of some mathematical papers, but yeah, to my best knowledge, I don't know some very rigorous multisymplectic reduction. And I have not elaborated, but there are some algebraic obstructions for constructing the L-infinity models. And we are just trying to understand the connections between another formalism, so-called de Dondorf formalism, which is suitable for the field theories. And I think it deserves to study. So to conclude, let me give some possible directions. So yeah, we can study on some curved target space, or we can extend to supersymmetry. And I'm also curious whether how to couple the background fields into this framework. And yeah, I'm also really want to know how to do some quantization in this setting. And yeah, it would be very interesting to study the spinning extended objects, which is the generalized version of the spinning point particle. And actually, this work started with to study the multi-coordinate orbits and its full classifications, but I think still the many stuff. I think it should be. I think we need some help from many mathematicians for now. So I hope to investigate these directions, and I hope you all enjoyed my talk. So thank you.
Questions?
Mm-hmm.
But I also remember that at some point, maybe in the 90s, the plasma experience,
Mm-hmm. Maybe, yeah. Uh-huh. You mean the commutator square?
Yeah.
Mm-hmm.
The way that people got rid of the problem.
I see.
Yeah. Exactly. So I was wondering if it's something we see after we come out of the
I think it is not that natural with this formation. Yeah. Number brackets. Number brackets. Yeah, at least, yeah, conceptually, I think it is related because number brackets allow some ternary or more brackets. Yeah, I think to study it, at least I think we need to gauge fix the time directions and in this case, maybe time and some, we should some gauge fix the worldsheet direction, and then we should study whether there's a connection between number brackets. Yeah, I'm also curious about that. Yeah.
What's a multi-coadjoint orbit?
To explain it, I think I need to explain from some coadjoint orbit and then multi-coadjoint orbit, but yeah, so maybe let me discuss later. Yeah. Actually, I don't have good idea what to answer for that, but at least one naive intuition is that such L infinity algebra can relate it to some, I don't know. Yes.
Imagine just using this action
Mm.
and just proceed
The
the
quantization.
usual.
Mhm.
Suppose if I put it in F integral,
And
I would repeat dx.
yes.
We take from it the result of F integral.
Right, right.
Try to slide. You have to have the standard of
Yes.
as a result of F integral.
Right.
So you imagining something like that when you say quantization or entirely different types?
We have not conducted the quantization, but we were implicitly do so another direction, not using the test integral. Yeah. I think it is more practical to study the quantization in that direction, rather than just mathematically uplifting these Poisson brackets into some commutators or something. Yeah.
But I mean, once you look at the integral, you don't really have a choice there. It's not like test integral exists, canonical exists, one follows from the other.
Yes.
The other way around. If you just take this as some quantitative set of variables and the test integral, it will imply some
Quantization.
quantization.
Right.
For example, canonical conjugate moment of X is going to repeat with you partial derivative of something.
Right.
So you end up with some composite, which is your canonical conjugate.
Right. Yeah, but yeah, I think it deserves to study in that direction.
All right. More questions? Yeah. If not, let's thank Kyungsun again.